Axiom welcomes you to a demonstration of its Honeywell G36 APU repeatable assembly process. You will see how Axiom allows you to get direct control of a process and part dimensional measurement data variation. Axiom's APU repeatable assembly process always provides an optimal straight build from the existing parts on the first pass that is well within run-out specifications, eliminating the need for rebuilds, improving engine performance, and reducing assembly time at minimal cost. Axiom's family of repeatable assembly processes generates many benefits that will result in significant, permanent shop cost reductions, improved EGT margins, and impressive fuel savings. Axiom has an extensive family of products and repeatable processes ranging from a simple low-cost starter kit to a family of repeatable assembly processes. The starter kit allows operators to measure parts and generate optimal rotor build models. Operators would continue to use the engine manufacturer's assembly tooling and procedures. Axiom's starter kit is upgradable to a repeatable assembly process in the future by adding Axiom tooling, software, and procedures. Axiom's repeatable assembly processes provide optimal straight build assemblies for individual rotors, high side and low side assemblies, geometric balancing assemblies that distribute blades about the rotor's actual center line of rotation, bearing compartment static structure and seal assemblies, casing alignment and assembly, and EGT margin and specific fuel consumption assembly process packages to maximize engine performance. All of Axiom's repeatable processes result in predictable assembly time, quality, and engine performance. Axiom's repeatable assembly processes provide consistent benefits to the engine shop and airline that are not available with other alternatives. Axiom's repeatable assembly processes put you in control of process variables and allow operators to consistently produce optimal builds on the first pass. There are 3 stages to achieving repeatable, high-quality engine assembly process. These stages consist of development of a predictive build model, the implementation of that build model, and the ongoing maintenance of repeatability and process stability. The control of variables, part measurement accuracy, and data processing are crucial to generate an optimal predictive build model with timeliness. Axiom provides a number of tools, software, and procedures for use in a shop's assembly area. Axiom provides a number of scalable gauging systems that range from small tabletop gauges for use with APUs to very large floor model gauges for certain industrial turbines. All gauges deliver measurements with at least a volumetric accuracy of 20 millionths of an inch, automatic tilt and centering software, and part distortion correction software. Axiom's high-precision gauging software provides measurement data at an accuracy required in engine core assembly. Each Axiom gauge measures concurrently with 4 probes. In addition, special rotor assembly measurement data is generated that contains part distortion correction. Measurement data is displayed both numerically and graphically in either English or metric. Part distortion is mathematically corrected by the biplane deviation software. This software simulates the part measurement as if the part were in a constrained state, as in a rotor assembly module being tested in a test cell, rather than a free or unconstrained state. Axiom's tilt and center mathematical algorithms are accurate to 1 millionth of an inch. This Axiom software, together with gauge tooling, allows part setup and measurement in about 4 to 5 minutes. Axiom provides a full set of gauge, tooling, or fixtures to hold parts and rotor assemblies for measurement. The SmartStack software computes from the best measurement data, a 3D homogeneous vector best fit of the parts, resulting in an optimal straight build. In Stage 2, the implementation of an Axiom repeatable assembly process, an operator will use Axiom's custom tooling software and procedures to build a rotor assembly that matches the predictive optimal build model from Stage 1. Axiom's family of predictive application software consists of Smart Stack software to build optimal straight rotors, Shaft Mate software to optimally mate a rotor to a rotor or a rotor to a shaft, Bearing Stack software to optimally align and build a bearing compartment static structure and dynamic parts, Smart Case software to assemble the casing and align its center line with the center line of the rotor and shaft, and SuperStack software to optimally build straight rotors and then distributed blades about the actual center line of rotation of the rotor assembly. Parts program software contains part geometric information that is essential for calculating the best fit assembly. Axiom designs and manufactures custom hydraulic assembly tools. To date, this type of tooling has been developed for over 100 engine modules. This tooling ensures proper seating of the rotor parts and prevents shifting of the parts in a test cell. Consequently, Axiom-built rotors do not fail in a test cell due to vibration. A detailed illustrative manual of procedures is provided for measurement, marking, and assembly of parts using Axiom's tooling, equipment, and software, resulting in a repeatable, stable process. In order to ensure ongoing stability, repeatability, and optimal performance of your assembly process, Axiom provides installation and training in your shop so that the process can be operated independently. Training typically lasts 1 week, depending on which processes are being utilized. Axiom's technical service and support programs provide 24-hour assistance and immediate response to any issues. Axiom provides 3 levels of service and support, depending upon your expectations for process performance and uptime. Under the Premium program, a 99% uptime at peak performance is guaranteed. Axiom certifies its measurement gauge systems, hardware, and software with a 3D master that emulates the geometry of the parts in the assembly. This master is the only approved method for gauge system certification by OEMs and the FAA.
Here is shown the engine cross-section. When overhauling this engine, this rotor design has the compressor and turbine overhung from the bearings, making the assembly very sensitive to alignment and balance. The problem of rotor assembly is compounded by having a small diameter shaft to compressor turbine, resulting in a 7:1 diameter to length ratio of the assembly. This results in the center line of the rotor components being severely affected by the perpendicularity of the compressor front face and the parallelism of the oil seal plate. As an example, for every 1/10,000th of an inch, or 2.5 microns, out of parallelism of the oil seal, the run out of the turbine nose increases by 1/1004, or 35 microns. These are some of the reasons that by using the Axiom assembly process that we will show you, you will be able to optimize your assembly the first time build and eliminate vibration and alignment rejects. The first part to be measured is the main shaft. The Axiom gauge uses the 2 bearing journals as datums and measures the centerline deviation of the compressor mounting diameter and the perpendicularity of the mounting face. These measurements are in both inch or millimeters. The second part to be measured is the compressor impeller. The gauge is datuming from the front mounting bore and face and measuring the biplane deviation of the outer ring mounting face and the center line of the inner ring mounting diameter. The geometry of the turbine is measured by datuming from the front mounting diameter and the mounting face. The turbine nose is measured for centerline deviation. One of the most critical parts in the rotor assembly is the seal plate. The parallelism of the 2 mounting faces have a large effect on the center line of the turbine when it is assembled. The part is measured for face biplane deviation. Once the geometry of the parts are measured, they can be automatically recalled into the Axiom SmartStack program. With a touch of a button, the software will compute a full 3D best fit of all the parts. When the computation is completed in less than 1 second, the results are automatically displayed on page 2 of the SmartStack program. The program will show at what angle each part should be assembled. The main shaft, being the first part, set at 0. The third page shows the computed centerline of each stage. When the unit is assembled, the centerline deviation should be very close to 560 millionths of an inch, or 22.4 microns. After the assembly computation, the parts are mounted to the gauge or any other device showing an angular position. The part is rotated to the angle computed by the SmartStack software. As shown here, the turbine is rotated to the prescribed angle of 85 degrees, and a white line is drawn. This line becomes the stacking axis to be aligned with the 0 on the shaft. The white number 54 is the last 2 digits of the engine serial number. Each part has the stacking axis marked in the same way as the turbine. The engine assembly is started by verifying the casing alignment to make sure the bearing center lines are the same as the static structure. This is done in order to maintain engine efficiency. The first step is to install the compressor into the casing. The next step is the turbine is installed, aligning the stack lines. Once the components are assembled, the turbine shaft is stretched hydraulically and the turbine runout is verified. The Axiom gauging system and its SmartStack engine assembly system is being used to assemble gas turbines that use both Curvic and Hearth couplings in their designs. You are looking at a typical APU compressor that has a Curvic coupling at each end. The compressor has mounted on each end a Curvic master. These are seated by a torque being applied to the center bolt. The compressor is then gauged for centerline deviation and biplane deviation. This photograph is showing the turbine being gauged while being mounted on a Curvic master. A Curvic or Hearth master is manufactured within a certain tolerance. These tolerances in both the axial plane and the centerline are generally very small, but can be as much as 50 to 80% of the engine part design tolerance. Axiom has an inspection program that determines the error in each master in both axial and radial directions. Once these errors are known, they can be added to the Axiom gauging inspection program. On measuring the engine part, the software will automatically correct the measurements for Curvic or Hearth master errors.
In summary, Axiom's repeatable assembly processes provide many benefits for the shop, including process stability, improved productivity, engine quality, and engine performance. The customer will benefit from improved fuel consumption, engine performance, and engine life. These benefits translate into significant ongoing cost savings for both the shop and its customers. This concludes a demonstration of Axiom's G36 repeatable assembly process.